Hello everyone, welcome to our new lecture of Discrete Mathematics. In this lecture, we are going to learn logical equivalence of propositional logic. So, what logical equivalence is? Let's assume we have two propositional logic, right? We have two propositional logic. We don't know what are these logics are. Just let's assume let's represent that this logic is x and this is y. Let's assume, right? We don't know what this logic actually are, but we are just assuming that this logic is x and this logic is y. So x and y will be equivalent if and only if for the same set of input or for the same set of possible values, x and y gives us the same truth values. So if x and y gives the same truth values for all the possible set of input, then we can say that x is equivalent of y. Remember, x, we are saying that x is equivalent of y. We are not saying it's not equal. X and y are not equal to each other, they are equivalent, and we represent the equivalent with this symbol. This is the symbol of equivalence. So what this giving the same truth values for all the possible set of input is, let's see. We already said that we don't know what x and y actually is. Just assume, let's assume that x takes four input. So this is one input, this is another second one. So let's assume x takes these inputs, right? So this is x, and as we said that if x and y are equivalent, then they will give us same set of output, same truth values for the same set of input. That means y is, if y and x are equivalent, then y is also taking the same set of input, right? So let's assume this is y. So this is y. So x and let's assume that x, for this set of inputs, x gives us this as output. We don't know how x actually giving us this output, as we don't know what x actually is. Just we are assuming that x give us this as output, right? So x and y will be equivalent if y is also giving us the same output. That means if x and y are equivalent, then y will be giving us the same output for the same inputs, right? So here we can see that x and y both are giving the same output for the same input, so they are equivalent. So now before solving, we also need to know few terms, right? We need to know three terms. One is tautology, one is tautology, one is contradiction, contradiction, and the last one is contingency. So what these terms actually mean? This term means that a logic is tautology if for all the possible inputs it gives us always true as output. That means whatever the input I give, it will always return the output true. So if all the outputs of an expression of a proposition is true, then we say that the proposition is a tautology. So what is contradiction? Contradiction is the opposite of tautology, which is a contradiction will give us output false for whatever the input is. That means whatever we give it as input, it will always return false. So if all the outputs are false, then it is a contradiction, and if all the output are true, then it is a tautology. Then what contingency is? Look, we said that tautology is when all the outputs are true, and contradiction is all the outputs are false. But there will be some cases where all the outputs are not true or false. That means the outputs are mixture of truth and false. That means there are both truth and false are there as output. So those cases or those propositions are known as contingency, right? So let's solve some example. Here we have a propositional logic which is a and b implies c by conditional a implies b implies c. So we need to show that this is a tautology, right? So we need to show that this is a tautology. So let's solve it and check if it is a tautology or not. So we have three input a b c, right? So the inputs will be true, 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 false, 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 false. So this will be true, true, so we know how to fill these values. So second, so let's fill up this table for this input, this sets of input. So a and b, so a and b will be true if both a and b is true. So here for these two case a and b are true, so this is true, this is true, right? Then these two will be false as b is false, so false, false. Then these four will also be false as a is false, right? So false, 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 false. Now we need to fill up this column, right, which is this. So a, now we have completed this part. Now we are completing this part. A and b implies c. So a and b implies c. If we complete, so this is a and b and this is c, so both of them are true, so this is true. This will be false as a and b is false but c, sorry, a and b is true but c is false, so this will be false, right? Then as this, for this 6 input a and b is false, so this will be automatically true. You can check the truth tables for implications or conditional statements to understand why for all these false values it's true. So then now we have completed these parts, but we also need to complete this part, right? So let's at first complete this b implies c. So b is true, c is true, so this is true. B is true but c is false, so this is false. Now this, in these two cases b is false, so this will be true automatically. After that here b and c both are true, so true. This will be false as c is false. After that these two will also be true. So we are done with this. Now we need to complete this. A implies b implies c. So this is B implies C and this is A. So we can see that A is true and B is true, so this is true. After that A is true but B implies C is false, so this will be false. Then these two will be true. After that these four will also be true as A is false, right? So we are done with this. Now we need to complete our final step, which is this biconditional part, right? So we are done with this part and this part. Now we are completing this final step. So this is A implies B implies C, this is A implies B implies C, and this is our A and B implies C. So they both are true, so this is true. After that they both are false, so this will be true. They both are true, so true. Then in this case is also true. Here both of, for this inputs, all both of them are true, so this is true. So now we can see that all the outputs are true. As all the outputs are true, so this will be a tautology, right? So now in this next question it is asked to show that this logic is contradiction. So we have already completed this part, or you can say that this part in our previous example. This was the example, so we already know the outputs of this part, right? That all of them are true. From the previous example we know that all of these are true. Now we need to show that this is contradiction. Now what's difference between this and this example? In the this was our previous example, this part was our previous example. So we have already done it. So I have just write the values. I have just wrote the values which are all true. Now you can see that there is a negation sign before this propositional logic. So as there is a negation sign, we know that if negation of true is false and negation of false is true, that means negation just flips our answer, right? So as this is a negation sign and all the outputs are true, so all these outputs all this result will flip in this final calculation, right? Because of the negation sign. So all the values will be, all the truth values will be false. So as all the values are false, we can say that this is a contradiction. Here we did not solve these parts as we have already solved this previously, so I just skip, but in exam you have to show this. So as I just skip because I just needed to show you the contradiction. What is contradiction? This is contradiction because all the outputs are false. So now we need to show what is contingency. We have already discussed that when the output is not all true or false, that means the output is a mix of truth and false, then it is contingency. So let's see if it is a contingency or not. So just fill up, let's fill the ABC. So we have filled the values of ABC, the inputs. Now we need to complete this truth table to show that this is a contingency, right? So let's at first solve this A or B. So as A and B both are true, so this is true. After that this is also true. Now A and between A and B, A is true. As A is true, so this will be true, this will also be true, and for these two it's also true as B is true. Now in this in this last two slots, both A and B are false, so A or B will be false, right? Now let's solve this part, let's complete this part. So this is A or B and C. Now we have already calculated A or B, So now we need to compute A or B and C. So both A or B and C is true, so this is true. After this, as C is false, so it is false. We know that when we do the AND operation, if one is false, then the result will be false. So this is false. After that, this will be true, this will be false, this will be true, false, 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 and this last two will also be false. Now we are done with these parts. Now let's compute B implies C. As B and C both are true, so this is true. After that, C is false, so this is false. B is false, so this will be true. As we know that if P implies C, then the truth table is when P is false, then the output will be true. If P and C both are P and Q both are true, then the output will also be true. It will only be false when P is true but Q is false, right? Only in that case P implies Q will be false. So here we are computing B and C. B implies C, so this will be true, this will be false, this will be true, this will be true. As B is true, false, then this will also be true, this will be false, as C is false but B is true. Now the last two is true, so these are true. Now we need to we are done with this. Now let's compute A implies B implies C. So A is true, B implies C, true, so true. A is true but B implies C is false, so this is false. After that, this is true, this is true. After that, A, for this last four, A is false, so this will automatically become true. So now what we need to do is, let's see, we have completed A implies B implies C, which is this, and A or B and C, which is this. Now we need to AND this, right? So if we AND, these are true, so true, these are false, so false. After that true, then this is false, so it will be false, true, this is false, so it will be false, false, false. Now you can see that here we have both true and false. These are true and the rest are false. So as we have both true and false in our output, so it is a contingency, right? Now we need to show that this propositional logic is equivalent to this logic. So we already know what equivalence is, so now we need to show that these two are equivalent. We can show that two logics are equivalent in two ways. One is we can show that using truth table, which is this, we can show using truth table, or we can prove it by using some laws. I will discuss these laws a bit later, but at first let's see how can we prove that two logics are equivalent by using truth table. So this is our truth table, let's complete it. So we have two input P and Q, so this will be the inputs, true, false, true, false, so true, false, true, false. So as now we need to compute this, right? So at first let's compute this not P and Q. So to compute not P and Q, we need to at first identify the not P, right? So not P is what? The negation or the opposite of P. So as P is true, true, false, false, so not P will be false, false, true, true. So now we need to compute not P and Q. So as these two are false, so these two will be false, as not P is false. Now in this case both not P and Q is true, so this is true and this will be false, as F is false. After that, now we are computing this part, not P or not P and Q. So we have not P and Q, and we have P. So as it is OR, so in OR, if there is at least one true, so the output will be true. So as P is true, so these two will be true, and in this case not P and Q is true, so this will be true. Only this will be the false. So now what we need to do, we have the negation parts left. So just we will negate this. So this will be false, 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 true. So we are done with this. Now we need to show that this is also gives us the same output as this, right? So P or Q, at first we need to complete P or Q. We have P and Q both. So this is true, this is true, this is true. Only this is false, as both P and Q are false. So the last part is not the negation part, so this will be the opposite, right? So false, 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 true. So now we can see that both this part and this part has the same output, right? This is F, this is false, this is false, this is false, this is a false, this is false, and only these are true. That means they gave, these two gives us the same output. So we can say that these two are equivalent to each other. So this is how we can show the equivalence by using truth table. We complete the truth table and show that both of them are giving the same output. Now we can also use logical equivalence. We can also prove logical equivalence by using some rules. What are these rules, sir? So this is identity law. In this law, if P and true, as we have said, that if it's need to be true, then P needs to be true. If P is false, then it will become false, as it is an AND operator. So P and true is P, then P or false is false, because the result depends on P. If P is true, then it will be true, and if P is false, then it will be false. That means the result is P. So this is identity law. Then domination law. Domination law is what? You can see that this is P or true, as it is P or true, and we know that in OR, if there is at least one true, then the output will be true. So you see that true is dominating here, so it is true. And P and false, in the case of P and false, it is false, as it is an AND operator, and there is a false, so false is dominating. Then idempotent law is P or P equal to P is equivalent to P, and P and P is equivalent of P. Why it is idempotent? Because both of the logic is P, both of the propositions are P. Now double negation law is what? Double negation law is we are negating twice. So at first when we will negate P, it will give us not P, right? And then when we again negate it, so that not P becomes P. So that double negation of P is equivalent to P. Then cumulative law, which is P or Q, equivalent Q or P. So you will find these laws in your books. So understand this from your books. I am not going to discuss uh, these laws here, but we will use these laws to solve, to show the logical equivalences. If we solve it by using laws, then we will use these laws, right? So let's solve one. This is P and P implies R, P implies R, and Q implies R, equivalent P and Q implies R, right? We need to solve it. So we can start from any of the side. We can start from this left side and show that this is equivalent of the right side, or we can also show start from the right side and show that this is equivalent of the left side. whichever you will find easy to solve. So I'm going to solve it from this right side, because I think this will be easier. So P or Q implies R, right? Implies R. So this, after that, now here let's see, in this law you can see that P implies Q is equivalent to not P or Q, right? So in this case this is our P and this is our Q. So P implies Q will be not P or Q. That means it will be not P, not P or Q or R, right? After that we will use the De Morgan's law. You can see that the De Morgan's law, this is our De Morgan's law. We have not, so you can see that here is not P or Q, right? So we can use this De Morgan's law, where is not P or Q is equivalent to not P and not Q, right? So we can write this part as not P and not Q, and this, and then this part or R, right? After that we can use this distributive law. You can see that this is not P or and Q, not Q or R, right? So this is the distributive law. Here P or Q and R is equivalent to P or Q and P or R, right? So in this case this is our P, this is our P, this is, let's assume this is Q, this is R, right? So we can write it as not P, not P or R and not Q or R, right? How did we write it? We write it from this, using this distributive law. Now from this part you can remember that we wrote, like, from here you can see that P implies Q is equivalent to not P or Q, right? So here we have a form of not P or Q, so we can write it as P implies Q, right? So instead of this not P or R, we can write it as P implies R, right? P implies R, and then this is the and, and then this part we can also write it as Q implies R. So you can see that we already got what we needed to show the equivalence. So we already got it. So we can say that this is equivalent to this. So the last example, we need to show that we need to show the negation of this, right? So the negation of this means that we have the expression P implies Q and R, right? So the negation means we have a negation before. So from this negation we can write it as this is a implies, this is a conditional statement, we can write it as not P or Q and R, right? We have already seen it, that how we that this and this are equivalent, right? After that let's use the De Morgan's law once again. Here this is in OR format, so you can see that the De Morgan's law here, not P or Q is equivalent to not P and not Q, right? So this is P or Q, this is P and this is q, and this is our negation, so we can write it not p and not q. So not p and not q and r. So this is equivalent to p, as we have already said that the double negation law. So this is p, and this not q and r, this not q and r, we can use once again the De Morgan's law, and we can write it as not q or not r. So this is the negation, this is the negation of this, right? So you can, we can solve this, but I'm not going to solve it, as uh, this is your task. You will solve, you will use a truth table and check that if this is actually the negation is or not. You can check it by using truth table. So that's it. Thank you, and subscribe my channel if you like it. Best of luck. Thank you.